Okay, so this will be the second part of the section that we're calling, what are we calling this section? Mechanical power and torque. And basically, we're going to work through this problem, which is example 5.2 on page 99. And so let's walk through that, and then we'll say that this section is completed. So let's do a little pause here. Okay, and again, make sure that you label this equation 5.6 in your text, that it's not labeled in the book. So make sure that you do your own label there, or at least make a notice of it if you don't want to write in your book. And he mentions right before we jump into this example 5.2 that it says equation 5.6 shows, equation 5.6, that we can raise the torque. We can raise the torque of a motor by either raising the armature current or by raising the flux. And either one of those will cause the torque to increase. Now, the Z number, of course, we can't really change that. I mean, once that's done, that's a design characteristic of the motor, and there's not much we can do about that. Okay, so now let's run through this example 5.2, and it says that the following details are given on a 225 kilowatt, and he says that that 225 kilowatt is approximately 300 horsepower motor. Now, that's a very large motor. That would be in a very robust type application where you're moving big things, and doing some real heavy lifting, so to speak, right? So this is a 225 kilowatt, 250 volt, 1200 RPM DC motor. And, it's given a couple of looks to us here. Of course, we're looking at it here, and, it's kind of hard to see that in perspective, but, that would be a diameter of 559 millimeters, or almost, half a meter. So that's a large motor. And talks about some of the particulars. There's some things that we know right off the bat. It has 81 slots, right? So it must have 81 coils and 81 commutator bars. So we learned that from some of our earlier discussions with the DC generator. And we remember that the generator and the DC motor are both built the same way. And here's some more pictures of, this 300 horsepower motor. And the one thing I really like to point out in this is, when we're talking about these coils, look at the size of these coils, okay? So they're very large. And as you can see from that coil picture there with this guy that looks like he's got a haircut from back in the days, my high school days, before all this left me and turned white. But anyway, you can see the coil, and when we're talking about that Z number, that's kind of what we're looking at. And this thing has multiple turns, and we can see those turns in there. So I like that picture because of that. And it's also showing, some of the actual labor that's involved in maintaining a DC machine. This is the commutator here. Here's where the coils are laid into the slots here, and all that. And they're really pretty amazing machines, but at the same time, they're expensive. They have a lot of copper. There's maintenance on them and so forth. And we'll find out later when we get into this three-phase induction motor that, there's a reason why the AC motor is so much more prevalent. But anyway, back to our example. That's our motor. Here's the armature and commutator, and it says that there are 243 coils, and that there are one turn per coil, and that it is a lap winding, and that there are 81 slots, and there are 243 commutator segments, which must match the number of coils, and that there are 6 field poles, and there's the diameter of the armature, and there's the actual length of the armature. And so we flip over to page 100, and he says, I want to find out what the rated armature current is. I want to know the number of conductors per slot, and I want to know the flux per pole. Okay, so this is what we do. You know, these are the types of calculations and problems that we work in a machines class. And so part of it's learning the language, understanding the construction of the machine, so we'll know what to plug in and what to solve for. You'll find the complexity of these problems much less than some of the complicated circuit analysis problems that you may have done in some of the other classes. So first thing we need to know, the induced voltage is, we assume that the induced voltage is very near the applied voltage. Okay, well, how would we know that? Well, this is the first time that we've come up on this, isn't it? So, you know, there's an assumption that we have to make, and it's given to us. So we know that power is equal to voltage times current. I'm solving this for current. So power divided by voltage, and we're given, you know, that, you know, we're talking about that everything in terms of the armature. So the only thing that we can do is make an assumption. And so what that leads to is this 225 kilowatts divided by the rated voltage that was given to us. And so doing that division, I would find the armature current running through all those coils is 900 amps. Now think about that for a minute. A lot of current, right? 900 amps. We haven't dealt with anything like that before in any of our other courses. And so machine and power, we look at things that are, you know, much larger in terms of currents and working voltages and so forth. Then he says, how many conductors are there per slot? Well, each coil has 2 conductors, he says, okay? He says there's just one turn. So when we're talking about it, this is 1 and this is 2, right? So, you know, that's where this comes from when he says that each coil is made of 2 conductors. And we also know that there are 243 coils altogether. So part B here, part B, I'll write it down here, 2 times 243 gives me a number of 486 total conductors. All right, how many slots do I have? Well, I have 81 slots. So I have to basically divide that by 8. And that tells me that there are 6 coil sides per slot. Okay, so I mean, you know, it's kind of sort of the same thing that we did before, just kind of understanding the language. Most of the time the information is given to you, you just got to put it, you know, think about how this thing is constructed, and you know, it works out fine. The motor torque is the power of a motor formula, this guy, right? This power of a motor formula, and what he's done on the second column there on page 100, he's taken that and solved it for torque, 9.55 times the power divided by the speed. Okay, so 9.55 is the constant. This is 225 kW here. And how do we know it's 1200? Again, that was given to us at the very beginning of the problem, right? It's turning at 1200 RPMs. So the torque will be 1791 Newton meters. Torque is always in Newton meters. And then the last thing he's asking us there, and let me get rid of something here so we can write on this. The last thing he says is, what is the flux per pole? Well, we finally have an equation for that. Where did I hide that? That's right here, okay? So now what I can do is I can solve this equation for flux, and I can come up with the answer there. So we're getting this really nice sort of library of equations that we can answer a lot of questions with. So the flux per pole, 6.28. Equation 5.6, solve for flux divided by Z times I. You plug in all the numbers, 6.28. We got torque over here. I'm not exactly sure why we're 1791 in the solving and putting 1790 here, but just so this works out and we're consistent, I'm going to write down what he has there. And say here's 1791, here's 1790, but anyway. And then the Z, the total number of conductors is 486 that we just figured out. And then the current is 900, okay? So all of this divided out, I'll slide it right here and give us our answer. Comes out to be 25.7 milliwebers. Not a unit that we deal with much, and not something that we have a lot of history with, or is that a lot or whatever, but you know, that is the answer for the example 5.2. And again, this problem and the one before that we worked in the section before, very typical of the types of problems that we will work. Everything is equation based. If we weren't doing this online, you would be developing, and I would require it and want to see it, is a formula sheet, and you'd have all of these formulas listed and all this, and you would actually carry that in when it came exam time and so forth. But anyway, we're not doing so much of that right now. We're kind of coming at this different, but just think about that and think about all this being equation based and making sure that you know what these equations are, when to use them, what every variable stands for. Let me quit talking. I'm done.